right, here we go. So I have a number of theorems here, and then examples that follow them. We're going to be learning how to use some of these theorems about circles. The first one, theorem 1213 says if two chords, so we have two chords crisscrossing in the center. Does this kind of look like a plus sign to you? Okay, you have to use your imagination. Sort of, look at things.
Wait, where's slanted?
Right here, slanted. So if the two chords crisscross in the center, then the measure of either one of these angles, we're going to go with angle 1 here, is equal to this half the sum of the measures of the two arcs here. So that's why I was asking, does it look like a plus sign? For this theorem, if the chords crisscross on the inside of the circle, then we're going to add these two arcs and then divide by 2 to get this angle. Now, if I know this angle number 1, would you agree that I could also find the measure of this angle equal, right? Why is that? Vertical angle. And same thing would work here. If I knew AC and BD, I could add these two up, then divide by 2, and it would give me these angles. Okay? So that's what the first theorem says. So if I want to find the measure of angle 1 in example 1a, it's going to be equal to 1/2 the sum of the two arcs it intercepts, so 90 plus 122. So you're going to add those two together and then divide by 2. So take and add up 90 and 122. What do those two add up to?
112.
212, okay. So we're going to take 1/2 of 212. Which is 106 degrees. So if you have two chords that crisscross in the center, just remember they make a plus sign, sort of. That plus sign should remind you to add up the two arcs and then divide by 2, and it will give you the measure of this angle. How does example 1a differ from example 1b?
The 1 is not where it's a different place.
The 1 is in a different place. It's not part of that. If I were to draw a line through the arc and the two vertical angles in the other arc, they all line up here, right? But here they don't. So what I'm going to do is maybe find this angle. Let's call it angle 2 first. And then if I know what angle 2 is, it's going to be supplementary of angle 1. All right? So how will I find measure of angle 2? I'm going to take half of 135 plus 70. That's right. So half of 205. So measure of angle 2 equals 102.5 degrees. So measure of angle 1 equals 180 degrees minus 102.5, because angle 1 and angle 2 are supplementary. And that ends up being what? 77.5 degrees. So that's the first of many theorems about circles. Supplementary angles will always add up to 180, yeah. So once you know one of these angles, these two are vertical, and then these two are always supplementary. So you can find all 4 angles around that one vertex. All right, so there's a reason why I'm focusing on if they crisscross in the middle to make a plus sign. Well, if they come together outside, you don't add them, you actually subtract the arcs. So any questions on this? Before I go to the subtracting line. Okay, here's what the subtracting one says. If you have, you'll see in just a minute here. if you have two secant lines, these are called secant lines, they go through the circle, they don't have endpoints on the circle, that's a chord. The two secant lines, or a tangent in a secant line, or two tangent lines even, that meet outside the circle, then you take and subtract the two arcs that I'm highlighting in green, and then divide by 2 to get this angle x. So when the two segments meet outside of the circle, you're going to subtract the two arcs that it intersects.
Subtract the arcs.
And then divide by 2. So in this case, if I call this, say, A, B, and this was C, D, what we're doing is taking measure of angle x equals 1/2. Got a room here. Try that again. That's not going to work either. So it's measure of angle x equals 1/2 measure of arc AB minus measure of arc CD. So very similar to the previous theorem, but we're subtracting that. Now, this is the smaller of the two arcs at 92. You have an idea of how I could find the other arc, the big arc that these two tangents intersect? If I put a dot here, put a dot here, this is the 92.
Oh, you minus 360.
What's that?
360 minus 92.
All right, 360 minus 92 will give me the measure of the larger part, which is 268. So you first have to do a subtraction from 360. Now once I know the bigger arc is 268, now I can use my formula here. Measure of angle x is equal to 1/2 measure of the big arc. So the big arc is the 268 minus the measure of the little arc, 92. What's 268 minus 92? 176. Okay, so 1/2 of 176. Half of 176 is 88 degrees. That tells me x right here is 88. Any questions on that? One of the big themes this year has been use a geometric theorem or definitions to set up an algebraic equation and solve it. So we're going to have a whole bunch of those coming out in this lesson. For example, right here, I've got measure. Need to write measure here. What's going to take the place of measure of angle x in this problem? 40. 40 was, 40 degrees equals 1/2. The big arc is 140 minus the little arc is x. Now my variable is at a different location, so I've got to do some algebra to solve this. So here we go. By the way, we will be having a quiz on this. It's going to be everything through this lesson. Next week, either Monday or Tuesday. I'll let you know.
It's like 12:45.
I'm going to hold off on that. That'll just be on the short-line test. But the quiz will just go through 12.4. 12.1 to 12.4 are a bunch of definitions and theorems and how to use them. So finding lengths and so they'll kind of go together.
So now this is a virtual test.
I will give you a list of these theorems. You can do that. These are pretty obscure theorems that unless you're studying circles, you're probably not going to be real familiar with them. I remember. So we have 40. Half of 140 is 70, and then distribute the 1/2. There are a couple of them that you don't need to memorize the theorem. You can actually use similar triangles. I'll show you that one that's coming up next. That's the type of thing I would put on your finals when we don't even need the theorem. You just use the idea of similarity. All right, so if I subtract 70 from each side, I have negative 30 equals negative 1/2 x. What's my final step here in the algebra? Multiply each side by negative 2, that's right. So 60 equals x. And this right here is 60. I'm going to set this one up down here. Any questions on that one? No? All right, see if you can tell me what goes, so what's going to take the place of measure of angle x in this problem? X over 2. So the x over 2 is the actual angle. The other two are arcs. Equals 1/2 of the big arc. So what's the big arc's expression here? X plus 70. Now I'm going to use a bracket here and then parentheses x plus 70. So that represents my big arc minus the little arc is x plus 30. You see why I'm using the brackets and the parentheses? What's happening right here? Yeah, I would deal with all combined like terms here before you get into the rest of it. When you distribute this minus sign, the parentheses say make sure you hit both of these terms with the negative. So it looks like this: 1/2 x plus 70 minus x minus 30. On the left-hand side, I have x over 2. So look what happens to the x's here. They cancel out, yeah. So I have 1/2 of 70 minus 30 is 40. X over 2. So x over 2 equals 1/2 of 40 is 20. And multiply each side by 2, and I get x equals 40.
Where you want one is not where you want it.
That's about what you're going to say, because the 2 is in the bottom, and I want
So you multiply both sides.
Yep. Multiply both sides by 2 here and here. This 1/2 I already applied to get the 20.
Is
Multiply.
that the same on the denominator?
Yep. Yeah, as a matter of fact, b, this negative 1/2 x is the same as negative x over 2. You can write it that way. So, any questions on that one? A lot of algebra to be done. Could be. I'm going to give you a theorem now. You'll have to be able to do the algebra. So here we are. Danger. So I'm going to read the danger circle from here. Scary. So do you know what a danger circle is? What's that?
Nobody wants to read it.
Nobody wants to read it?
Andy wants to
Oh,
read it.
Daisy will read it. Go for it.
The danger circle is the area of the sea where a ship is in danger from hitting rocks. Lighthouses are set up to warn ships. They create a circle with their arc and shown below. If the boat travels inside the circle, it is in danger. If the boat is outside, as shown below, it's okay.
Right. So they can actually, using degree measurements, figure out if it's safe or not. If that looks scary. Captain, look at it.
Those rocks really look
That's
scary.
terrifying.
Shark, squid, this guy. I don't know what he's doing in the danger circle.
Hanging out.
everything dangerous I could think of here. There's the danger circle. So the idea is this. Let me move this down a little bit. Put one there. We'll put one right here, maybe. And then I got to get my boat down here. Down. So it says that JC read this is 120 degrees from here over to here. So if I drew my inscribed angle, this goes back to our geometer sketchpad idea. If I go from my central angle to my inscribed angle, and so I take this central angle, which was right here, and I pull it out here, what happens to this angle in relationship to where it was? Does it get smaller or bigger? Smaller, right? So if this is 120 right here, what would this be according to my inscribed angle theorem from last time? 60 degrees. So what did it say the boat's reading was when you took the reading between the bow and basically between the bow and the lighthouses? It's 55. So what does that mean about the boat in relationship to this circle? I'm going to take, it should be outside because that means I'm going to take this angle and stretch it even farther out, right? You with me? If this boat's angle measured 60, he is right on the verge of entering the danger circle. So if we pull it out here, though, and we end up with an angle measurement here of 55 degrees, then that means there is an arc right here with the degree measure, so he's not right on it. As a matter of fact, we could find the degree measure here using our theorem that we just went over. It would be 55 equals 1/2. Let's call this right here x. So 120 minus x. Can you go ahead and find what x must equal if he's out at the 55 degree angle? Do a little bit of algebra here. What would x have to be? You might be able to do it by guessing chat.
Where's 60?
60 would be, the 60 would be right on the circle. If he had measured 60, he is sitting right here.
Okay.
But they said he's measured 55, so that means he's out a little farther.
So
Now, I was just showing you in relationship to what we talked about last time. If he had measured 60 degrees or anything higher than that, he's in trouble. He's already in, he's on the circle or about to enter, or already in it.
I don't know if doing this right if I got 5.
I think it should be 10.
Yeah, I do.
Well, how do we do the algebra?
I got 10.
So 55 equals half of 120 is 60 minus 1/2 x. Subtract
Oh,
60. So negative 5 equals negative 1/2 x. And here we go again, multiplying by negative 2, right? Multiply this by negative 2 and that by negative 2, and you should get 10. So that just means that there is a little bit of a degree measure or arc measure here.
Wait, does this mean that he knows that he's going to the circle, or is he?
What's that? Well, we're just saying he's sitting out at sea.
So he came from.
Yeah, as of right now, if he's not moving. If he gets any much closer, he's in trouble. He happens to be safe at the present.
Do all lighthouses do that?
What's that?
Do all lighthouses do that?
Yeah, they do things differently now, but that was the idea back in the day. Yeah, is they could use a chronometer of some sort, some kind of degree measurement device. Measurements, but yeah, I don't know today. To be honest with you, I think they probably have sonar reading and stuff like that they're using. We go visit lighthouses when we're on vacation. There's probably some uses for them still. There are probably still ships that use them, but I don't know what they're.
They look cool.
Yeah, some of them are actually. Yeah. The function isn't necessary anymore. Okay. This theorem, I actually introduced this to you a while back ago because it was showing up on the SST, and I wanted to show you how you could do problems like this without using the theorem. So I'm going to show you one more time here. Who's counting minutes and seconds? So, not yet.
After this.
Theorem 12.15 says if two chords intersect in the interior of a circle, so these two chords intersect inside the circle, the product of the segment lengths of one chord, so if you take this segment length that I highlighted in red times this segment length that I highlighted in red, it will equal this segment length times this one. That's what the theorem says. So your question should be, why is that?
Why?
Wait, so does that mean like for A, 6 times 3 would equal 9 times X?
Yep, that's what that means. For A, that would mean 6 times 3 equals 9 times X. So 18 would equal 9X, so X would equal 2. Super easy to use. But going back to Kira's question, you know, why does that work? Well, if I draw in this right here, and this right here, let's just go ahead and do this. We have this triangle and this triangle. What's special about those two triangles?
They're right.
Not necessarily right.
They're green.
They're both green. That's because they're both
Same.
not the
Not
same.
scale.
They're clearly not the
Same
same.
scale.
Same scale. What do we call that?
They're not
Similar. They're similar. As a matter of fact, okay, why are they similar? You can tell me that. By which similarity here? They will be. We got to prove first that they're similar based on their angles. Okay, there are vertical angles that are congruent, so you've got two angles that are congruent. Now, what about angle A and D? What do you notice about angle A and D?
Looks like.
What's this?
Oh, they both.
Okay, right here, that intercepts arc BC. And this one intercepts arc BC, right? So this angle is congruent to this angle is congruent to this angle. That's all we need. It's angle-angle similarity. So by angle-angle similarity, these triangles are similar. Therefore, I can say EA is, I gotta erase this again. Let's just do this and this. If I put EA, it corresponds to, say, EA over what does EA correspond to in the bigger triangle? EA goes with, oh, I lost it over here. So EA, are you with me here?
EA goes with.
ED. So EA is to ED as EA. If I were, these two triangles are similar right here and here. If you were to flip this one over and then dilate it, shrink it down, they would match up perfectly. So EA goes with ED, and then we need to involve EC in this. What does EC go with? ED. Now, that's by similar triangles. Watch what happens if I cross multiply here. Look at that. Magic. Can you believe it, Rio? Look at that. I cross multiply here.
Witchcraft.
Practically. So EA times EB, look at this. Right? And ED times EC is this. So this theorem is based on similar triangles. Based on similar triangles.
Pause. Now it's not. Oh, my legs.
Okay. So using this theorem is pretty easy, right?
Yes. Yeah.
You can use the theorem.
It's over.
It was a nice 5 seconds.
You guys have been exercising. You guys have been exercising. So we have 6 times 3 equals 9 times x here, and then we solve for x. Now look what happens in part B. If I use the theorem, I've got 2 times 4, right? You know, I'm going to move it in just a minute, but that's where my hint is hidden in terms of what to do. So 2 times 4 equals what? Ooh, and then the games began. What kind of formula or equation, I should say? What kind of equation do I have when I multiply 3x times x minus 1.
Agree.
Yeah, it's a quadratic. So how do I solve a quadratic? You actually have two choices, factoring or quadratic formula. You actually have a third, it's called completing the square, but quadratic formula takes the place of completing the square. So let's move our little hint over. So keep in mind quadratic formula. So 2 times 4 is 8. 8 equals 3x squared minus 3x. If I'm going to use the quadratic formula on this thing, what do I need to do first? Yes, minus the 8 to the other side. It has to be equal to 0. So I'm going to subtract the 8 over. Otherwise, you won't have the right sign on your c that you're plugging into the quadratic formula. Okay, so we have 0 equals 3x squared minus 3x minus 8. So now let's solve for x. X equals negative b, so positive 3 in this case, plus or minus the square root of b squared will be 9 minus 4 times a is 3 and c is negative 8 all over 2a. So have your calculating devices ready. What is this under the radical equal? See the minus, and then we're going to have a negative number, right? So minus a negative number, we're going to end up adding. So 9, 4 times 3 is 12. 12 times negative 8 is negative 96. You're going to end up adding that to 9. So it's 9 plus 96 over 6, or x equals 3. I'm going to hold off on the plus or minus sign. Is it really true that both the plus and minus will create values that will work for x? Let's think about it for a minute. If I did 3 minus square root of 1 of 5, can you give me an estimate of square root of 1 of 5? What's the whole number estimate? 11 or 10. Okay, so either of those would be acceptable. If I do 3 minus, say, 10 here, what kind of number do I get? Negative 7 divided by 6, still negative, right? Not going to work. So I can drop the negative sign, just leave the plus. Okay? So 3 plus, I need some calculations done. 3 plus square root of 105. What's square root of 105? A little better than what is 10.2. Okay, add that to 3. 13.2, yeah, and then divide by 6. Got 2.2. Okay. So x is about equal to 2.2. I don't see any units here, but that's the only solution that's going to work. So the geometry was easy. The algebra was a lot of work. Well, it takes, I would call it perseverance here. Anytime you're using the quadratic formula, it's going to take some work.
Are we going to do the next thing again?
The x thing again. Yeah, earlier when we first approached this problem period 2, we said, okay, can we go ahead and use this and see if we can factor it? We're looking for factors of 8 times 3, or negative 24 that add and equal negative 3, and we couldn't find any. We listed all of them out. You'll notice that none of these factors add up to equal negative 3. So factoring doesn't work. It doesn't work all the time. Quadratic formula does work all the time, yeah. For getting a solution or even for identifying if there's no solution. But factoring not always. Factoring is only going to work if you have a rational solution. All right, theorem 1216. Kind of similar to the previous one. It says that 2 secant segments meet outside of a circle E, then the products of the secant segments and their external secant segments are equal. here's the external secant segment. It's just saying that, okay, watch as I highlight. If you take this piece times the whole thing here, that'll be equal to this piece times this whole thing. That's all that's saying. Let's see if we can apply that to example 6a. So what would EA be in this example? So I have 9 times, what would EB be? Not 99. It's gonna be 9 plus 11. So we have 9 times the whole length. So you're gonna have to add pieces together. Equals the outer one 10 times the whole thing 10 plus x. And I've created more algebra for you to do. What kind of a equation is this one? If I distribute here, I have 10 times 10 is 100 plus 10x. That's x to the first. So at least this one's linear, right? It's linear. It's not too bad. It's not a quadratic. So 9 times 20 is 180 equals 100 plus 10x. Distributive property.
So ABA,
Subtract 100 from each side. 80 equals 10x. Finally, divide by 10. So x equals 8. Does that look reasonable? Why did I do 9 plus 11? Because the theorem says multiply this segment, the outer segment, times the length of the whole segment. To get the length of the whole segment, I got to add it. Because of the last theorem, a lot of students want to multiply those numbers, but that's not how you get the length of EB. So x equals 8. That looks reasonable. It's kind of difficult to make pictures like this and get them to be to scale, but if it's at least in the ballpark, then you're probably right. But I have to warn you that our pictures on all these on quizzes and tests and things like that, and skill tests won't necessarily be to scale. I think we see that even in this one, but we did the best we could. So B here, what's the setup on B? For this guy, we've got outer is x times the whole thing. Now this time I'm giving you the whole thing. Yep. Equals outer times the whole thing, which is 40 plus 38, or 78. Because the theorem says take the outer segment times the whole length. The 72x equals 40 times 78. I don't know. What's 40 times 78? 2,120. And then divide that by 72. 43 and a third. So that seems reasonable, at least. If you get something like 6 for x, so that would be a question that it's at least kind of in the range.
Can we just do 43.3 and then put the y in?
Sure. Just round it to the extent.
Yeah,
43 and a third is exact. That's what 0.3 with the bar over it means.
I don't want to or use about
wait. So
or
You're not concerned about your fair share.
I don't like that.
Oh my
for
god.
the one
No, that's not it.
There's more?
There's more.
Yeah.
Okay, go ahead.
for the 1/3. So it says so the 3 with the bar over it. Wouldn't that end up if you add all the would that be just 9 with a 9 bar over it? That's how full number.
No, the 3 with the bar over it. 0.3 with a bar over it.
Yeah, and then if you add that times up by 3, that would be 9.9 and the following rate, and that wouldn't be the full number. You get it?
No.
I'm making it complicated. Never mind.
I'm not.
All right, this is the one that's on your SST right here. I'm gonna give you right after this. It says that I think of this one as the same as the previous theorem. It says if you have a secant and a tangent. Okay, watch carefully on this. Hang in there. Almost there. It's the last kind of long, difficult bit. It'll actually be nice because you can just do them after that. Listen to me. I don't. This isn't like something that lends itself to self-discovery. This is something that gets better to explain to you. So EA, here we go. This segment right here times the whole thing, that's what the left-hand side of that says, is equal to the outer segment times the whole thing. It just so happens that the outer segment and the whole thing on a tangent segment are the same thing, right?
So it's C times C. So it's EA, sorry, EC times EC.
It's EC times EC is the way I think about the right-hand side of that. Yep. So if you apply that to example 3a, we've got EA is actually X, right? What's EB here? From here to here. Yeah, 4 plus X or X plus 4, not to be confused with 4 times X, right? And then equals, the outer segment is
I squared.
yeah, and then the whole segment is also 5. I actually don't worry about the squared. I just treat this like it's the previous theorem. Right, 5 times 5. What's that? Because I think of EC as both the outer and the whole from the previous theorem. They happen to be the same.
Why would it always be?
I don't know why. I don't know why. The first letters in the alphabet. Yeah, I don't know. That's probably why. So I have. What happened here?
Oh, no.
So x squared plus 4x minus 25 equals 0. So somebody factor this for us? Are the factors at negative 25 that add to equal 4? What are the factors of 25? No difference of 3 there. What are the other factors of 25?
1.
No difference of 3 there. Are those all the factors of 25?
Yeah.
Rats.
Oh no.
What do we have to do then? Yeah, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So x equals negative 4 plus or minus square root. This ends up being a positive number. 4 times 1 times negative 25, that's negative 100. It's 16 minus negative 100 all over 2. So that does equal a positive number. It's square root of 116 all over 2. Guess what you get to do with the negative part of that plus or minus? Yeah, because negative 4 and then subtract the number that's between 10 and 11, it's still negative. But negative 4 plus a number somewhere around 11 is going to be positive. So what do we get here? Okay, and then subtract 4 from it, so 6.7, and then 6.7 divided by 2 is 3.
We just leave it at 3.
Okay, about 3.4.
Can we leave it like that?
No, we should find the length.
Oh, that's so
Because otherwise you can't go, does 3.4 make sense for that picture? I mean, if I look at this, -4 plus square root of 116 over 2,
that makes more sense.
Yeah, the diagram there or something, there has to be something.
TPG.
Or
Nope.
guessing, like.
Right,
guess
or
stuff.
formula.
pretty low probability you're going to guess it.
Like, between 4 and 5, I think.
Kira could have, but she's got superpowers. The rest of us, though, that's just what is it?
No.
So this is 10. I don't think so. Square root of 116.
12.4.
Square root of 116 is not that big.
Oh, that's
I think it should be about 3 point something. All right. This one's got 2 things going on here. How do I find x? You recognize it.
Oh, 12 times x and 8
Yeah.
equals 8.
12 times x equals 8 times 18. That's the easy thing. Now it's easy. 12x equals 144. So x equals 12. Yeah, that one's easy. We got our x.
Why?
Why is this new theorem? So if this is 12 right here, we know the outer segment 2 times the whole thing. What's the whole thing here? Not quite. Let's write it out. 12 plus 12 plus 2.
Oh,
26.
26 is right. Equals the outer segment over here, this tangent, times itself, which ends up being y squared. So I've got 2 times 26 equals y squared. So 52 equals y squared times 26 is 52. So y equals plus or minus the square root of 52. Only one of those makes sense for this problem. So y is, we use squiggly equals here, approximately equal to the square root of 52, which is 7.2. There's our y.
maybe.
We're going to explain this. You'll need to write down the homework assignment here. There aren't a lot of problems. You might have some that involve factoring or quadratic equations.
Like, I already know it, but just make sure, right? Like, the b plus or minus, like, whatever.
Oh, write the formula down? Sure. Yeah, you might want to write this down on your sheet. X equals negative b plus or minus square root b squared minus 4ac all over 2a.